Hello, everyone. Welcome back to linear algebra. This time we're in section 3.5, inverses and inverse mappings. Okay, so we're going to talk about inverses of matrices. Okay, so I should put at the beginning here that A is a square matrix. Okay, so we only discuss inverses for square matrices. So a lot of matrices don't have inverses because they're not square. So only the square ones, but only some of the square ones have inverses. So let's describe what we mean by an inverse. So it's just like for numbers. We start with a matrix A, and we're considering whether it has an inverse. So we're looking for another matrix B of the same size. So let's write that down here. So B is also n by n. Okay, such that the product is the identity matrix. Okay, so here I is, because A and B are n by n, the product's n by n, so I is n by n. So it's not written there sub n, but that's what it means, n by n identity, which means it's one down the diagonals and all zeros. Okay, so it's that diagonal matrix with ones down the the main diagonal. Okay, so that's acting like our number one in terms of matrix multiplication. Remember that? So our symbol for the inverse matrix is a to the -1 power, but note a minus 1 does not mean 1 over a, okay? It's just a symbol for the inverse of a matrix. Okay, so AB equals the identity, so also the reverse order is equal to the identity. So if you have one, you have the other. Okay, so we don't have to write them both down, but they are both true if you have an inverse. So let's look at an example for instance. So a 2 by 2 example. So if A is this matrix 1, 1, 1, 2, I claim that the inverse of this matrix is 2 minus 1 minus 1, 1. And to show that, we simply do the multiplication. So let's do A times this candidate, 2 minus 1 minus 1, 1. Okay, so when we do that matrix multiplication, as you can see, I'll go first row, first column, I'll get 2. Sorry, am I missing a minus 1? Yep. I'll get 2 minus 1, so I'll get a 1 there. And then I'll go across the second entry in the top row of the product. So that's the 1, 1, top row of 1, the first matrix, 1, 1 dotted with minus 1, 1. I get a 0. Now I'll go to the bottom left corner. So that I'm on the second row of the first matrix, 1, 2 dotted with that. I get 0. And now I go to the last entry. So the bottom row and the last column, I get minus 1 plus 2, I get 1. Okay, and then you can check that the other order of multiplication also gives me the identity. Okay, so that means that matrix here that I wrote down is indeed the inverse of A. We also want to make a note here that A is the inverse of the matrix A to the minus 1. So A is the inverse of this guy, right? Because this is true, right? So in other words, if you find a matrix such that, or two matrices such that their product is the identity, two square matrices, then they are inverses of each other. Okay. Now the inverse is unique, so there's only one, just like for numbers, and some properties of matrix inverses. So let's look at what happens when you combine inverses or questions about inverses with scalar multiples of matrices, products of matrices, and transpose. Okay, so how does the inverses relate to those? Okay, so let's look at this one I'll call A, B, and C. Now remember, we want to show that the inverse, that these statements are equal, which means that, for example, this first one here, A, says that the inverse of TA is -1. So I'll write that down in English just once here. Okay, so A says that the inverse, maybe I'll use my blue here. Okay. Okay. The inverse of TA is this matrix here. Okay, so it's 1 over T times the inverse of A. So just because we wrote down this equality here, and I have this symbol A to the -1, it already means that the A that you see in this equation is invertible. So A is invertible. Okay, so I don't have to say that before I start to write down the sentence. It's tacitly assumed. Okay, so A is invertible. All right, so how do we show that? So we need to show that, okay, if I take this matrix, TA, and the candidate inverse, so the statement A says that this 1 over TA inverse matrix is the identity. We need to show that this equals, sorry, is the inverse. So we need to show that this product is the identity. Then A is true, okay? Because A is claiming that the inverse of TA is this 1 over T times A inverse. So we just have to do the multiplication. So verifying that a matrix is the inverse of another one is very easy to do. The hard work, as we'll see below, is looking for the inverse. Okay, so this is not about looking for the inverse. It's about verifying that a given matrix is the inverse of another given matrix. Very easy to do. You simply do the multiplication. So let's do the multiplication. Okay, so, well, I have TA, okay, times 1 over T. Let's do it all at once. Now, to the -1. Now, these are scalars right here, right? These two numbers. So using the properties of matrix multiplication, scalar multiplication, I can bring those T's, those two scalars out and multiply them together. All right, so I bring them out, and then I have these two matrices. Okay, so this is property matrix multiplication. Okay, and then I do the multiplication. Good, so then I get 1. And then I have this product, -1, right? So this is, I don't have to write the 1 anymore, and A times A inverse is the identity. Okay, so it's true. So in fact, this matrix right here is the inverse of TA. We demonstrated that. Okay, so that's all you have to do. So let's continue on with the other two in the same manner. So it's pretty easy, but if you don't see what you have to do, then it's not very easy. Okay, so B is going to be, let's just write it out quickly then. B is claiming that the inverse of the product, okay, I'm looking at B up there, the inverse of the product is this product, B inverse on the left times A inverse, okay? So that's what the claim is. So to verify that the B inverse times A inverse is the inverse of AB, I'm going to multiply AB by that, which is B inverse, A inverse. Okay, I could do this product in the other order too. Okay, it's the same kind of calculation. So let's do this. Now that's a product of 4 matrices. So I'm going to use associativity. I'm going to, which means I can do the pairwise multiplication in any order. So I'm going to do the inner 2 first, right? And then I'll, okay, so I can do it that way. So when I put brackets like that, okay, here, sorry, when I put brackets like that here versus here, on the left, it's telling you to do the AB multiplication first, then the B inverse, A inverse multiplication, and then the final one. On the right, it says do the B inverse multiplication first, and then do the A multiplication, and then the A inverse multiplication, right? So the brackets are just telling you which order to do them, but matrix multiplication is associative, so any order I can do it. So I'm going to do it in this order, and if I continue on, I'll get A. Now that product is I. So once again, if you see in an equation like this, the symbol B to the -1 and A to the -1, it's tacitly assuming that A and B are both invertible matrices, okay? So B times B inverse is that. Now, you don't have to write, just like for numbers, I don't have to write a 1 between the product of two numbers, right? It doesn't matter. So I don't have to write the identity matrix there. So let's just take it out. And now I have these two to multiply together. And well, one is the inverse of the other. So it's the identity. So the product is the identity. So we verified that. Now let's go to the final one. The final one, C, is saying that the inverse of this matrix, A transpose, is A minus 1 transpose. Okay, so this one's a little bit more abstract, I guess. What I want to do now is recall something about transposes. So there's a property about transposes and matrix multiplication. It's this one here. I'm writing it out on the right. So the transpose of a product is the product of the transpose. Okay, you see that? So that's recall. So when I see this in front of us, I'm actually looking at that side of the equation. Okay, so I'm going to reproduce what it looks like when there's just a single transpose. So if you look at what I wrote on the right, you'll see that I should have this guy on the left, and then I should have this on the right, and then I should take the transpose. Okay, so that's that property I wrote on the right, exactly that. So using that, so I'm just rewriting the product of the two transposes as the transpose of this product according to the properties on the right. But then that's just the identity. But identity is equal to itself as a transpose. Okay, so we've done it. Okay, so those three properties we've established, not without, I mean, with little effort. Okay, we just had to verify that the matrices given to us were the inverses. And that's easy to do. That's just matrix multiplication. Okay, so that's three important properties of matrix inverses, algebraic properties that you'll be using regularly when you're using linear algebra. Okay, so let's try to find out for a while now. We're going to look for methods to search for inverses of matrices. And it's an involved process. I mean, it just takes time. We have a very well-defined algorithm to do this. Okay, so let's start with a matrix A. So let's just look at a 2x2 case. We're looking for an inverse. Okay, let's call the inverse this unknown matrix X. What property of X do we wish it to have? Well, we wish the product AX to be the identity. Okay, so I'm going to show you one way to determine the inverse of A by looking at this, what I just wrote down here, this matrix equation. Okay, so let's go. So we take an arbitrary matrix. Here it is. Okay, so I'm entering its 4 components as A, B, C, D. Okay, that's a D. I'm using an alpha later on, so I don't want to get you confused. That's a D there. Okay, so A, B, C, D. And then I have our unknown matrix X. So let's call its entries X1, X2, X3, X4. So you see these 4 parameters here. 4 of them are variables and 4 of them are 4 or 8 symbols, right? 4 of them are variables, 4 of them are parameters. The A, B, C, D are the parameters. That's a matrix A. So it's a matrix that you know. So in a concrete situation, we know the A, B, C, D. The unknowns are the X's, okay? So the way this works is you give me a matrix A. I see what the A, B, C's, D's are, okay? Then from that, I want to find X1, X2, X3, X4. So the X's should depend on the A, B, C, D. All right. And then in this situation here, 2x2 matrix, the identity that we're considering is the 2x2 identity. Good. So what is AX? Well, it's this 4x4, 2x2 matrix. It's right here. Okay. So you just do the matrix multiplication. Now I want AX to equal this 2x2 matrix. Okay. So that is a matrix equation, but to determine the equality of 2 matrices, we look at the components. So there's 4 components there, and I'm writing them out here on the left. So the top left component of AX is AX1 plus BX3, right? And the top left entry of I is 1. So that's why this equation arises. So that's the 1, 1 entry of AX equaling the 1, 1 entry of I. Now I go to the it looks like the 1, 2 entry of AX, and the 1, 2 entry of the identity is 1. And then I'll go down to the 2, 1 entry of AX, which is, sorry, which is, hold on, did I AX1, sorry. Did I write this down right? So that C, sorry, I see an error here, right? This is a C and a D, sorry. I hope this is not, should be fine, right? So this is now the bottom row, sorry, CX, let me see this. I hope I'm not getting this mixed up here. So it should be CX1, DX3, right? And then I go across, so AX2, BX4, and then CX2, DX4. Okay, good. All right, so I made a little mistake there in my notes, but it looks good. So CX1, DX3, so actually it's all okay down here. And then the 2 entry of AX, I can see is CX2, DX4. The 2 entry of the identity is that. Okay, so you see how I went from matrix equation to these 4 scalar equations, one for each component of the matrix on the left and the matrix on the right. Okay, this is how we compare matrices, how we determine they're equal. So what I've just written down is now 4 equations in 4 unknowns. Remember, the unknowns are the x's, not the a, b, c, d. So when we look at the augmented matrix, okay, that's this one here. That's the augmented matrix of that system. The columns are the x's. The A's, B's, and C's are parameters. So that's the augmented matrix with the right-hand side here. Now, I leave it up to you to row reduce this. Now, this is something a little bit more involved than you've seen before, but we've done some examples like that where we've row reduced a matrix with parameters, 1 or 2. And then along the way, we had to determine certain conditions on the parameter so that we can continue on with our row reduction. That condition is right here. It says that AXD minus BC is not 0, okay? So this had to be satisfied before we can complete our row reduction, okay? Because I see it there in the denominator. So if this condition AD minus BC is not 0, then you can continue on your row reduction until you reach this final row reduced echelon matrix. And you see there's a unique solution. And if I write it out, so x1 is D, x2 is minus B, x3 is minus C, xd is A. So if I put that into the matrix X with this 1 over AD minus BC coefficient, I call X the inverse, okay? So this is my matrix X that I started with, but because my product equals the identity, I've labeled it as A inverse, okay? So you see the logic of that, and it is possible to do this yourself if you want to sit down and work a little bit for that. Okay, but now there's a simpler calculation to allow us to find determinants for larger matrices. For the 2 by 2 matrices, this would be the formula to remember, I'd say. So 2 by 2 matrices. You remember this formula to tell you the inverse of a matrix. And then also this formula is telling you this, that this is the condition that the matrix has an inverse, that A has an inverse. And that is that quantity is the determinant of A, which we will see later on, okay? The determinant. So you take a 2 by 2 matrix, you compute this product, AD minus BC. Notice the order of the A, B, and CD. It has to be as I've written here, okay? So A and D are the diagonal and C and B are the anti-diagonal. If that quantity is not 0, then you immediately write down the inverse as this. Now, the inverse matrix, it's not hard to remember, okay? If you think about it, you see that compared to A, you first reverse the order of the diagonal entries. You see that? So in A, you had A at the top and D at the bottom, but here you have that backwards. Now, the anti-diagonal entries are in the same order, okay? But you've added minus signs to them, okay? So if you can remember that, then fair enough. But if you can't remember that, you know, it's something like that, you can just check that your product should equal the identity, and you'll figure it out pretty quickly, okay? All right. So for larger matrices, though, there's not such a simple formula. Okay, so we're going to now describe the algorithm which works for all matrices, even 2 by 2 ones, okay, but for any matrix that will eventually produce the inverse of a matrix, or it will tell you that the matrix is not invertible. Remember, some matrices don't have inverses. We saw it on the first page, and some do. It's not easy to tell just by looking at them. But in this algorithm where you're aiming to find the inverse, it will tell you if there is an inverse or not. If there is an inverse, you will find it. If there isn't, you will reach a point where you realize that it's not invertible, the matrix. Okay, so here's the algorithm. You build this compound matrix, which means you adjoin two matrices. So you start with the matrix A. Remember, A is n by n, and I is the n by n identity. Okay, so you have this matrix, two next to each other. And we usually put that straight line down there in the middle. You don't have to. Now, what size is this matrix? So the number of rows is n, but the number of columns is 2n. Okay, so it's the two n by n matrices next to each other. And then we row reduce it. Okay, so let's just practice doing that row reduction. So once again, row reduction, this important idea of finding inverses boils down to row reduction, like many things do in linear algebra. So here we go. So this is what we mean by this compound matrix. This is our A. It's a 3 by 3 matrix now. Okay, so I plug in A on the left, and I plug in the 3 by 3 identity on the right. Now I row reduce, and I should emphasize here, you're row reducing the A. You're not paying any attention to the I, but you perform the same operations on the same row operations on the right one. So row reducing A, but perform same row operations on the right side matrix, okay, which starts out as the identity, but it changes as you go through. All right, so this is the idea. So you're only concentrating on A when you're doing the row reduction, okay? So the matrix on the right is not playing a role in the row reduction. So I've set it up here, okay? Now, I've made some row operations here, okay, in the next sentence. So you can see what I did. So for example, here, I multiplied the first row by 1/2, right? So I got a leading one there. I multiplied the first row of my A by 1/2. Therefore, I do the same thing to the matrix on the right. Okay, so that's why it's a 1/2 there. Now for the second row, I created a 1 here by dividing the second row by a quarter. Okay, so I divided the second row by a quarter, you can see that. And therefore I divide the second row on the right by a quarter. Okay, so I'm just mimicking the same row operations I've applied to A, and I haven't done anything to the third row. Okay, so now I move down. The next thing I want to do is eliminate this one in the bottom row. Okay, so how did I do that for A? Well, I subtracted the second row from the third. Okay, so subtract the second row from the third. This is what you end up with in the third row. But I do that also to this row. So I subtract the second row from the third, and that's why I get this. Okay, so you see what I did on there? I did the same row operation to the third row of the matrix on the right as I did to the third row of the matrix on the left. Okay, now I keep on going. So I'm working my way down to row reduced echelon form of the matrix on the right. I'm almost there. So here's what I do now. I did a couple steps. So this 1/4 I made into a leading one. So I multiplied the third row by 4. So let's first look at that. So I multiplied the third row and the one above by 4. That's why I got this here. All right. Then I went to eliminate this 3/4. So what I did is I subtracted 3 times that new third row. Okay, so subtract 3 times the new third row, and you will get this matrix here. Okay, so the top row I didn't change. Now this is row reduced echelon form. It's the identity. Okay, so I have I'm finished with my row reduction. So I reached the identity. What I have on the right then is the inverse matrix. Okay, so I've just pulled out what I have left on the right there, and I claim it is the inverse, which means that if I do this matrix multiplication, okay, it's easy to see that I will get the identity. So it must be the inverse, right? They're unique. So if you get it any old way, even if you guess it, if you can guess it, and you check that this product is the identity, then you found the inverse. All right. So in summary, we're doing the following. We're row reducing this augmented matrix or compound matrix. Yeah, compound matrix, that's the proper way. To A goes to the identity. So when I've row reduced A to the identity, I've changed A, the identity, which was on the right, into the inverse. Okay, so that's the summary of this algorithm right here. You form this compound matrix and you aim to row reduce A to the identity. Okay. So what happens though, if the row reduced echelon form of A is not the identity, if you cannot achieve this in the row reduction, okay, so the row reduced echelon form is unique to a matrix. There's only one. And for square matrices, it may be the identity, it may not be, okay? So if it's not, then that tells us that A is not invertible. So for example, this one down here, I want to check whether this matrix here on the left is invertible. So I plug it in on the left. I have 3 by 3 identity on the right. Now you can do the row reductions and you'll see this matrix A I started with, that's its row reduced echelon form right here, okay, which is not the identity. Okay, so it's not the identity, and therefore this matrix is not invertible. And if it's not invertible, we call it singular. Okay, so that's some terminology for you. Singular, okay, means not invertible. Okay, so this algorithm will do two things. It will tell you whether or not a matrix has an inverse, and it will also give you the inverse if, in fact, it does have an inverse. And this algorithm is the same process no matter what the size of A is. So you could go back to the 2 by 2 matrices. You could find inverses of 2 by 2 matrices two ways. You could remember this formula, which is convenient, as you'll see. It's convenient to remember that formula. Or you can just apply this algorithm here, which works for 2 by 2, but also other sizes. There's no simple formula like this for the, I mean, there's a formula, but it's not simple, okay? This is the simple it gets for 2 by 2, okay? So for 3 by 3 and bigger, the formula, and you could look it up in the book, is formidable, okay? So it's much easier to do this algorithm we did with the compound matrix. Okay. So that's what you will find if you do the same process with this abstract matrix. This is done in the book, okay? And then you will also determine that you get the same formula here, okay? So following that process, which means I plug in A, B, C, D in the 2 by 2 identity. If I row reduce, I row reduce the left-hand side to the identity under this condition here, not being 0, I can row reduce it to the identity. I will end up with the formula I found above, which is right here. Okay, so that's the way they did it in the book. Let's use that formula here just to see how, show you how it can be done. Here's a 2 by 2 matrix. Okay, so first thing I do, I want to determine whether this matrix has an inverse. I compute this determinant, as we'll call it. So notice it's the product of the diagonal entry, okay, minus the product of the anti-diagonal entry. So I get 6 times 7 minus the product of -4 and -4. So it's 26. So it's not 0, it can be any number, but if it's not 0, it's invertible. And therefore I pull out that formula right above us here. So the inverse is 1 over 26, 1 over this determinant. And then I did that property where I reverse the order of the diagonals, right? And then I take the negative of the anti-diagonals. Okay, so if you can remember that, then it's easy to write it out. And you can check that this answer is the inverse. So in other words, multiply this against A, and you'll see you get the identity. Okay, so that's that other way to do this. Find the 2 by 2 matrix inverse. Okay, now armed with that knowledge, we can talk about what role inverses play in solving linear equations. Okay, so this is interesting to see. Just recall that if I have a certain type of system of linear equations, now this must be a square system. Okay, so I'm talking about a square system of linear equations. And by square, I mean the number of equations is equal to the number of unknowns. So you see I have n equations and n unknowns. Okay, so that's a square system, what I'm calling a square system. And the reason I call it square is because the coefficient matrix of that system is n by n. Okay, so the coefficient matrix, you know what it is. It's the numbers appearing in front of the x1 to xn in each equation. And using that coefficient matrix, I can rewrite the system this way. Okay, so remember, this is a convenient way, a compact way to write down any system of linear equations. For us here, we're talking about square systems. So this matrix A is square. Okay, X is the column vector of unknowns, and B is the column vector of the right-hand side. Okay, now let's bring in the inverse of A if there is one. So if A is invertible, okay, it doesn't have to be, remember, if A is invertible, then we treat this just like we do in algebra with numbers. Okay, so I'm going to write that down on the right here. Compare with, here's the a similar equation in algebra with numbers, right? Something times x equals something. So the matrix one, I have a known matrix A and a known right-hand side B. Here I have a known number 3 and a known number 2. And what we do, you divide by 3, but really what you're doing is you're multiplying, and let me do that in the same color. You're multiplying both sides of the equation, although we don't typically think about it, right? We just go ahead and do it by this inverse of this number 3. Okay, so I do that, and then I do that product, okay, which isolates my x, and then I do the product there. I mean, I'll just write it out now. So inverse of 3 times 2, we typically write as 2 over 3. Okay, so 2 over 3. So that's how we solve that equation. So I'm going to do the same thing for the matrix equation under the assumption that it's invertible. So I multiply both sides by the inverse. Now remember, unlike for numbers, the example on the right, I have to make a decision. Am I putting the A inverse on the right or the left of a matrix? And for us, we're putting it on the left because I want to eliminate the A. Okay, it's the A I want to eliminate. So I'll multiply both sides of that equation here. Okay, since they're equal, if I multiply both sides by A inverse on the left, I'll still get an equal. All right, so what do we get when we do the multiplication? Well, there's my A inverse multiplying the term on the left. There's the A inverse multiplying the term on the right. All right, now I do like I did before with those properties of inverses. This is a product here. This is a product of 3 matrices. Okay, so I'm going to do the first 2. I'm going to use associativity. So the first 2 matrices I'm going to do first. And I'll just leave this as that because that's all we can say. And then when I do this multiplication, of course, you see that that's the identity. Good. So I get the identity, the n by n identity. I don't have to write the n there if you understand how big the x is. Okay. And then just like for numbers, I don't have to write like here in front of this x here, I did not write the number 1. Okay, it's there, but I don't have to write it. So I don't have to write the identity matrix because the identity times x is x. All right, so this is what we get, and therefore this is the solution, is this product. So I write out this product and I get my answer. I've solved a system of linear equations in one matrix multiplication. Okay, this is under the condition A is invertible. So there you go. A very concise and compact way to solve linear equations of this size, square linear equations, under the assumption that A is invertible. If A is not invertible, this is not the solution. In fact, you can't write A inverse. Okay. What we see here, I'll make an observation. The solution is unique. Now remember, I should also say this, the system is consistent. And, all right, because remember, when you start with a system of equations, right-hand side, non-homogeneous one, so B is not 0. Okay, so I'm under the case B is not 0, there's always the question about consistency. Is there even a solution? All right, so here, this B could be 0, okay, but if it's not, I still have this question about consistency. But if A is invertible, the fact that I can write out my solution here tells me that there is a solution. So it's consistent to begin with. And because x is equal to this vector, there's no other vectors that x is equal to. It's unique. Okay, so I get both those pieces of information under the condition A is invertible. When A is not invertible, both of these can fail. Well, it won't be unique if it's not invertible, as we'll see later. Okay, so keep that in mind. It's not unique if it's consistent. So let me write this out. Here, food for thought, later. Food for thought. Okay, if A not invertible, then, now here we have to answer the consistency questions. I'm going to just say that it's consistent. So then if system is consistent, okay, so we can talk about solutions. Solution is not unique. So there's many solutions. Okay, so that's what happens when the matrix A, and remember this is just a square system, okay, because we can't talk about whether or not a matrix has an inverse if it's not square. So in this case where the square matrix is not invertible, and there's many matrices that are square matrices that are not invertible, when the system's consistent, right? Remember, it doesn't have to be consistent even if A is not invertible. So that's a question. So I'm assuming it's consistent. If it is, the solution is definitely not unique. Okay, so there's many solutions. So that's an important feature that we'll be reminded of later on. Okay, so I'll put it here so you can think about it. Okay, so we're building up a nice long theorem of equivalent statements, which you should contemplate from time to time as you go through this course, just to remind yourself about how things are connected. I've said to my class that the concepts in linear algebra are intertwined in many different ways. So it's a really good way to learn in linear algebra, is to look for these relationships, these connections between concepts. So statements like this, where we have a list of equivalent statements, and I'm explaining what equivalent statements mean. So A to K, there's K statements there. It means that any one of them implies the truth of the others and vice versa. Okay, so there's many statements here actually. If you wanted to prove this, there's many things to do. I won't do all that. But this list of equivalent statements is a good way for you to learn the connections between the concepts, okay? So I don't think I would ask you to memorize this and repeat it on a test. That's not worthwhile. But you should learn to understand this, and you will use these as you proceed through linear algebra, because certain properties will appear and then you'll be able to reinterpret it in another way. Okay, and that's going to be very useful. So I'll just say a few things here and then leave it up to you to contemplate this on your own. So for example, trying to prove these, okay? So that's a good thing to do. So let's try A implies B, right? So that's only one direction of the double implication, A if and only B, right? So this is only one of them. Why is that? Why does A invertible mean that the row reduced echelon form is I? Well, we go back to that algorithm, which was item 5 above. Okay, so item 5 told us that, right? Because item 5 was that algorithm with the compound matrix. Okay, and we saw that if you can row reduce the matrix A to the identity, the matrix on the right side is the inverse. Okay, so that's item 5 above. What about A implies C? Do we see how that works? So A invertible implies the rank of A is N. What do you think of that? Well, if A is invertible, then its row reduced echelon form is the identity. That's the B part. So I'm actually going to go through B to get this. So let me just write this out here. So the RREF of A is IN. Okay, so that was the A implies B. And that's how we determine the rank. Okay, that's one way to determine the rank. It's the number of leading ones in the row reduced echelon form. Remember, that's one way. The rank is really the dimension of the column space. Okay, but this is an equivalent definition. So what is the rank of the identity? Well, it's clearly, this is the square one by one, the square identity matrix. It's clear that every column has a leading one, so its rank is N. Okay, so the rank IN is in is n. Okay, so that's why that's true. Now let's group together these three at the bottom. So, or sorry, these ones right here. D, E, and F, you see them? They're all about equations. AX equals 0, AX equals B. Okay. Let's see why A, because the way this theorem is stated, all statements are equivalent. So A should imply all of these statements, D, E, and F. Okay, so A, let me write it down here. A implies D, E, and F. Okay, so in other words, if A is invertible, then these are true. And I was alluding to this discussion just previously. So A implies D. Okay, so inverse of A implies what? The trivial solution. So AX equals 0 has the trivial solution only. Wow, this equation, I would just multiply on the left by A inverse, right? Okay, and therefore that equation just tells me X equals 0. Okay, so just using the fact that A is invertible, I can write down that the solution is just the 0 solution. There's no other solution, all right? So when A is invertible, I see that the only solution of the homogeneous problem, okay, that's a homogeneous problem, D, as only the trivial solution. That's an important notion for us, okay? It has to do with the dimension of the null space is now 0, and using the rank dimension theorem, the rank nullity theorem, the rank is n, okay? So that tells us that the dimension of the null space is 0. In other words, the kernel has only the trivial solution in it, trivial vector, the 0 vector. Now for E, I have now, I'm assuming it's a non-homogeneous problem, okay? And it has to do with consistency. Remember, there is the consistency problem. That's a very important problem in linear algebra. It's not specific about finding solutions. It's just asking whether there are solutions, and that's very important in applications just to know that. So what we see here is that if A is invertible, then this non-homogeneous system, and remember it's a square system, so it's just a particular kind of system of equations. Nevertheless, square systems of equations, non-homogeneous, can be inconsistent. But if A is invertible, this is saying that that's not true. It cannot be inconsistent. It must be consistent, and for any B. So it doesn't depend what B you've got there. It's true for all of them. And that's simply the same calculation as above. That is, if I have AX equals B and A is invertible, I'm just going to multiply both sides by this A inverse, and then I get this answer, X is equal to B. The fact that I have the answer means it's consistent for every B, and actually F is combined in that one too, because I see, so F is also dealing with this non-homogeneous problem. I see that there's only exactly one solution, okay? I mean, this is it, X, sorry, not X equals B, X equals, I forgot my A inverse B, right? It's that vector, okay? It's usually not looking like B. Okay, let's try something else that doesn't use A in it. Let's try D implies what? D implies G, okay? Let's see, D implies G, right? Okay, I just mentioned that too, right? So we can say something about the null space of A, which follows from what we know about the homogeneous solution, has only the trivial solution. So because D implies G and A implies D, we also have A implies G. So that's how you can work your way through these statements. I can go to A implies G through the A implies D and D implies G. Okay, so using this formulation of that implication, this says that if A is invertible, then the null space is the 0 vector. Okay. A implies, sorry, A implies G. Yeah, A implies H. Okay, let's do that one. So A implies H. Now, notice H is about the transpose. A implies H. Okay, so H says that the null space of AT is 0. Okay, so what do you think of that? Okay. Well, A saying A says A is invertible. So A invertible, and we've seen above with the properties of the inverses with respect to the transpose, we saw that if A is invertible, then I have a formula for its inverse. Sorry, the inverse of AT, which means that AT is invertible. Okay, so remember that formula up there was AT inverse is the transpose of the inverse. Okay, that was the formula we saw up on the first page even. So that is telling us that the transpose is invertible. So A says A is invertible. Therefore, the transpose is invertible. Okay, I know that from that property. And therefore, the null space of H is just the zero, because the null space of A being zero just follows from the fact that that matrix is invertible. So AT being invertible means its null space is zero. Okay, so that's how you would look at that one. And do I have any more? JKL. I don't, oh, I'm missing one here actually. Yeah, how come my sheet here, hold on, is missing one. So I think there's, yeah, okay, let's just include it on here, okay? So I'm gonna finish up this lecture with something a little bit more abstract. So instead of matrices per se, we're gonna be talking about linear transformations, okay? So linear transformation. This is a very important theorem here. Okay, so let's recall a linear transformation. So that's a mapping from an Rn to an Rm. But here we're taking Rn to be the domain and the codomain to be Rn. So the standard matrix is n by n. Okay, so remember this is the standard matrix of L. Okay, so that was described in the previous lecture. Right. So if L is going from Rn to Rn, then its standard matrix is an n by n square matrix. Okay. Also recall from the previous lecture the notion of inverses of linear transformations. It's just similar to what we did in calculus for the inverse of functions. So if you have a linear transformation like this, T, so have an L and I have a T. Okay, so start with an L and I have another transformation from Rn to Rn. I form the composition, L composed with T or T composed with L. These are both defined. If that composition is the identity function. So the identity function is the following. It's this function which doesn't change the vectors. So its domain is Rn, its codomain is Rn, and it just takes x to x for all x. That's the identity function. Doesn't do anything, okay? Then we call L to be invertible. So it's an invertible, just in the sense of functions, it's invertible. And we call this transformation T its inverse, okay? So instead of writing T like I did there, we'll write L to the -1. Okay, so just like functions in calculus, we know that if I compose a function with another that gives me the identity function, then that other function we call the inverse of the one we started with. Okay, so in this case, we say the linear transformation is invertible. Okay, and we write this. So this is just summarizing that. Okay, so if L is invertible as a transformation, then when I compose it with its inverse, I get the identity. Okay, now, before we move on to the theorem, we make one more observation. The standard matrix of this function, this identity function, is the identity matrix. Okay, so make sure you check this. Okay, the standard matrix of the identity function is the identity matrix. Okay, so check that. That's an important observation. And that leads us to this very important theorem that we will use. Okay, if L is invertible, okay, so I have the assumption that is invertible, then I know two things. I know that its standard matrix is has an inverse. That's this part right here. Okay, so the box L is the standard matrix, so it has an inverse, and that matrix happens to be the matrix of the inverse transformation. Okay, isn't that interesting? So that's a very important statement right here. Okay, make sure you understand and appreciate what that's saying. So maybe I should add here two things, right? Because this one sentence kind of puts them together. Two things. So under the assumption that the transformation is invertible, remember transformation is just a function, it's given to you by a formula. So this theorem is telling us two things. If that function, that linear transformation is invertible, then its standard matrix, which is an n by n matrix, is invertible. Okay, so that's an important fact already. Okay, the standard matrix is invertible, and its standard matrix is the matrix of the inverse transformation. The inverse transformation is also a linear transformation. So it has a standard matrix. So this theorem is saying that that matrix is just the inverse of the standard matrix of L. Okay, so the proof is pretty simple once you understand all these concepts. Okay, so let's look at this proof. Now it uses this very important relationship between composition and matrix multiplication. So read this very carefully. All right, so on the left it says the standard matrix of the composition of two transformations, M and L, okay, is the product of their standard matrices. This, by the way, is why matrix multiplication is the way it is for us, okay? That complicated formula, row dot column, this is why, so that this theorem is true. So is why matrix multiplication is defined the way we defined it. Okay, otherwise this theorem wouldn't be true. Is why matrix multiplication is defined the way we use it. Okay, so the way it is used here. Okay, all right. So that's a theorem, and that takes a little some thinking to look at. But it's not a long proof, but it's a little bit abstract. But that's an important fact. So so how this is used is if I already know the matrices, the standard matrices of two transformations, and if I can compose them so they have the right size, the codomains and the domains, then I already know what the standard matrix is of that composition. It's just the product of these two matrices. I already know the standard matrices of the two transformations. So it saves me work in computing the standard matrix of the composition. Remember, it takes time to compute the standard matrix. In this situation where when you already know the two matrices, the two standard matrices of the transformation, you simply do the matrix multiplication to get it. Okay, so that's a fact that we use here. Okay, so let's continue on with the proof. Thus, I have this particular composition. So I'm assuming L is invertible. So there's the two linear transformations I'm considering. One is L, one is L inverse. Okay, so this property now tells me that it's equal to this. So I'm just using that property here. Okay, so the standard matrix of this composition, L and L inverse, is the product of these two. Okay, but I also know that because I'm composing L with this particular linear transformation, which is the inverse of itself, that the composition is actually the identity function. And I know the standard matrix of that linear transformation, it's the identity matrix. So when I plug these two equations together, I see that the product of L, the matrix, standard matrix of L and the standard matrix of L inverse is the identity. Okay, so I'm just looking at the right-hand side of both equations. So, and that tells us, as we know from above, if I see a product of two matrices that's equal to the identity, two square matrices, then they're inverses of each other. Therefore, this matrix L inverse, the standard matrix of L inverse, is the inverse of the matrix L. Okay, so it's actually a very short proof, uses this powerful theorem 3.2.5, which is a little bit abstract, but not too much. Okay, but and then a very simple calculation to prove this. So very nice result that the matrix of the inverse of a linear transformation is the inverse of the standard matrix of the transformation. I'll do one example. Okay, but make sure you do some more examples in the book. Whenever you can compute the inverse linear transformation and find its standard matrix, then you can do it two ways. You can compute it from the way we compute standard matrices, and then you can compute the inverse of the transformation L you started with, because you know how to do that now, and you will see they are the same. Okay, so let's do it with an example which is pretty easy to determine what the inverse transformation is. I'll take a rotation, so R theta, that's a linear transformation, it's rotation by theta, and its standard matrix, so box R theta is this, as we know, that's the standard matrix of it. Okay, fine. Now, we know geometrically that the inverse of this transformation, okay, is just rotation backwards. So in other words, if I compose those two, I get the identity transformation, and which means I don't do anything, right? So when I compose those two together, I first rotate by theta, and then I rotate by minus theta. So the net result is nothing, which is the identity transformation. So I know what the inverse linear transformation is to r theta. It's simply r minus theta, rotation by minus theta. Good. So let's compute the matrix of, we're going to compute two things. We're going to compute the matrix of, the inverse of r theta, and I'm going to compute the matrix of r minus theta and show that they're the same. Okay. So let's first do this. What's the inverse of the r theta matrix, which is given right here above? Well, that's a 2 by 2 matrix. I'm just going to use our formula for the inverse of a 2 by 2 matrix right here, right? So it's 1 over AD minus BC times this thing here. So for this matrix here, the r theta, okay, the AD minus BC is just cos squared plus sine squared. It's 1. So this is an invertible matrix. And then I do that property of, I change the order of the diagonals, which they're the same, so that's fine. Then I take the negative of the anti-diagonals, which I did here, okay? So this is the, this thing over here. Well, actually, it's just this one right here now, okay? So that's the inverse of that matrix, okay? Now I'm going to write it as, I'm going to plug in a minus theta there and keep the same formula. Because cos is even, the cos theta is equal to cos minus theta, right? Cos is even, so I'm going to write this down. Cos is even. Cos is even. All right. And sine is odd. Okay, so so cos theta and cos minus theta are the same. So that's how I've done that. And then sine minus theta is going to be minus sine theta. So minus sine theta, I write as sine minus theta. And then sine theta, I write as minus sine theta. Okay. Now, that's actually the standard matrix of our minus theta, right? Okay. So I've shown that the, I'm done because I showed that the inverse of r theta is the matrix r minus theta. Okay, so this is demonstrating this theorem right here. Okay, the matrix of the inverse transformation is the inverse of the matrix of the transformation. Okay, so take a look at that. It looks pretty sleek and simple, but that's a little bit dangerous because you might not get it. All right, so I think I'm done with this lecture. So I will see you guys later. If I can turn this off. Yes. Stop.